Hello everyone, I welcome you all to today's video. Today we are going to understand the difference between linear and logistic regression. Then we are going to see how gradient descent is used to optimize the parameters. We are going to understand these topics by solving certain questions of assignment. My name is Manas Pathak and I'm a student of IIPS DABB. So let's start. The question for today is differentiate logistic regression and linear regression on the basis of hypothesis, parameters and cost function. How gradient descent algorithm is used to optimize the parameter. So basically first we have to differentiate the logistic regression and linear regression on the basis of given 3 points, which are the hypothesis, parameters and cost function, and then we are going to see how gradient descent algorithm would be used to optimize the parameter. So let's first understand these differences. The hypothesis based difference. So hypothesis in machine learning can refer to the equation which is used by a particular algorithm to find the relationship between the independent and dependent variables. In linear regression, we try to find the define a linear relationship between the independent and dependent variables. Therefore, the hypothesis is a linear equation here. It fits a straight line or hyperplane through the data. The output can be any real number and is a continuous variable. So here you can see the equation which we use in linear regression is y equals to a0 plus a1x1 plus a2x2 till total number of independent variables are included in the equation. Here the values a0, a1, a2 are called coefficients or parameters. We are going to talk about parameters in the next point. Logistic regression, whereas logistic regression, the hypothesis is a linear equation wrapped in a logistic function. So basically what logistic regression does is it estimates the probability for a data point x or a tuple to belong to a particular class. So it calculates the probability which should be between 0 and 1. That is why we use the logistic function, because it forces the output to be strictly between 0 and 1. And as you can see the logistic function equation here, the function which is in power of e in both numerator and denominator is nothing but the function which we use in linear regression. Because linear regression for logistic regression, linear regression comes hand in hand, because while performing logistic regression, performing linear regression would be a prerequisite. So first, for any logistic regression problem, we would fit a curve that would best estimate the given data, and then we'll use pass the equation of that curve to our logistic function, which then forces the output which is between 0 and 1, basically, which it gives the probability for the data to belong to a particular class. So hence this is the hypothesis based difference between linear and logistic regression. Then the parameter based difference. So although we use the same function and same parameters in both linear and logistic regression, which is this equation which we use for linear regression, but there are still certain differences between parameter based differences between linear and logistic regression. A coefficient ai represents the direct change in output y for a 1 unit increase in xi. So here in this equation, if I increase the value of x by 1 unit, the value it would reflect the change in the value, the coefficient a would show the change in y when I increase the value of x by 1 unit. Similarly, it is used in logistic regression, but in logistic regression, it represents the change in log odds of the outcome for 1 unit increase in probability. So basically, the function which is passed to the logistic regression is called log odds. So when we make a 1 unit increase in x, the like in linear regression, the value of y is directly implemented, and it is shown by using coefficient a. But in logistic regression, it does not directly impact the probability, but it represents the change in log odds of the equation. So I hope you understand that. Typically using ordinary least square method or gradient descent to minimize the squared error. So in linear regression, the typical method which is used for minimizing the squared error is the ordinary least square method. So least square method, as you must have known about it, it finds the it tries to find the minimum squared error for the given data. We can also use gradient descent and linear regression, but for logistic regression, we use gradient descent becomes a necessity because we use the minimum maximum likelihood estimation via gradient descent to maximize the likelihood of the observed class. So this is a difference between the two linear and logistic regression based on how the coefficients or parameters are found. Generally, linear regression uses the least square method, whereas logistic regression would strictly implement the gradient descent. Cost function based difference. A cost function is a function which is used to measure the error of error which is occurred by the model in making predictions. In linear regression, popular cost function for linear regression is mean squared error. It is simply the average or square of differences between the original values and the predicted values. The function is convex, bowl shaped, meaning it has single global minimum, and that is easy to find. So here is the formula for mean squared error. It is a cost function for linear regression. In mean squared error, we try to find the square of difference between the predicted and input or the real outcomes, and then we take the average of all those square values, which gives us the mean squared error. Whereas in logistic regression, binary cross entropy or the log loss function is our cost function. It is used in logistic regression problems. It quantifies the difference between the actual class labels and the predicted probabilities output by the model. So just like in linear regression, mean squared error is used to find the difference between the predicted and actual values. In logistic regression too, it quantifies the difference between the actual class to which a particular label belongs to and the predicted probability by the output model. The lower our cross entropy value, the better the model's prediction align with the true labels. So the binary cross entropy or the log loss function is designed such that whenever there occurs an error in the prediction in the predictions of our model, it penalizes them highly, so the value of binary cross entropy increases. So higher the value of binary cross entropy, that means our model is more poor at the performance, whereas lower the value, the better the performance of the model. uh, the logarithmic component of BCE function penalizes wrong predictions more heavily than correct ones, ensuring the function remains convex. So as I told you that there are heavy penalties for a wrong prediction than than the rewards for the correct prediction. So by using that mechanism, it implements the log x function basically. So log x function is such that the value of x lies between 0 and 1. So the more closer the value of x is to 0, which indicates a wrong prediction, the more higher the value of log x would be, and the more closer the value of log x x is to 1, the value of log x would be more closer to 0, hence the value of binary cross entropy would be less. So this is how the binary cross entropy is used as a cost function in logistic regression or classification problems, binary classification problems most likely. Now we are going to understand how gradient descent is used to optimize the parameters. It is a first order optimization algorithm. We can find the minimum of a convex function by starting at an arbitrary point and repeatedly take steps in the downward direction, which can be found by taking the negative direction of the gradient. So this is basically the algorithm of gradient descent, that we start from an arbitrary point, and from that point we start taking steps in the downward direction. We determine the downward direction by using the gradient. Gradient is basically the slope at the point which we are which is with us at currently, where we are standing correctly. So from that point we'll find its gradient or slope, and we'll go against the direction of slope. If the slope is positive, the against direction would be negative, hence we'll take steps back, whereas if the slope is positive, we'll take steps in the if the slope is negative, we'll take steps in the positive direction. That means we'll move ahead. After several iterations, we will eventually converge to the minimum. So gradient descent is a iterative process where we at each point we find the slope, then and after finding the gradient we go in its negative direction, and we do this iterations until we have reached a minimum. Now minimum in this case corresponds to the minimum value of the value of the coefficients, which gives us the minimum error. That is what we mean by minimum in gradient descent. In our case, minimum corresponds to the coefficients with the minimum error or the best line of t. The learning rate determines the size of steps we take in downward direction. So as I told you, in each iteration, based on our slope, we take certain steps in the opposite direction of the gradient. So we determine those steps by using the learning rate, which is the hyperparameter which is decided before the process of training starts. So this is how gradient descent would optimize the parameters by basically giving providing them such values for which there would be least amount of error for our cost function, or it finds basically the best line for our given data. So this was all about today's video. I hope you understood the topics covered. If you have certain doubts, you can drop them in comment section. I'll surely answer them. I would like to express my sincere gratitude to Dr. Shaligram Prajapat for guiding me throughout the semester. If you like this video, please consider subscribing to my channel and liking this video. I'll see you in next video. Thank you.